Hello, welcome to Chapter 7, Section 1. Oh my goodness, we're halfway through the book. So, in Chapter 7, we are talking about sampling distributions. So, this is the part of statistics where now we finally get into, all right, we are going to try to predict a population parameter by using a sample statistic. So, remember, the whole goal of statistics is to research something about the population, do a study or whatever. But then we don't want to actually study every single person in the population or every single item in the population. We're just going to take a small sample of this and use that information to try to generalize and try to predict for the whole population. So remember, the parameters and statistics are like the numbers that talk about a population and the numbers that talk about a sample. So we're specifically going to be looking at like means, proportions, things like that, that talk about the population versus the sample, or the proportions that talk about the population versus the sample. So in order to calculate those things, or in order to try to predict accurately, this is where the probability part of our class gets thrown into play as well, so that we are using math to like accurately predict things. Before we can start talking about all of these things, though, we want to make sure that we are using the same symbols together. So we've mentioned this before, but it was less stressed until now. So when we talk about population numbers, population parameters, we want to make sure we're using the symbols that are specifically for a population versus a sample. So when we talk about means for a population, we use the symbol mu. So the Greek letter that looks like an M looks like a U, read as mu. For a sample, a mean symbol that we use is the X with a bar on top, so X bar. So anytime you see those symbols, you need to know which one they're talking about, the population or the sample. For standard deviation, for a population, we use the symbol sigma. For a sample, we use lowercase s. Sometimes there's that little x there. It's not necessary, but we usually have it. And then I also want to talk about proportions. So proportions are just, fractions, percentages, decimals count as a proportion. For a population, we use lowercase p. And for a sample, we use p with a little hat on it. It's kind of like when we did y hat, when we used two variables, and that stood for like the predicted value of y. Here, it just stands for the sample proportion. So in this chapter, we're going to start looking at samples in general. So if we were to take a sample and maybe do that many times. So first, we want to understand sampling variation. Sampling variation just means when I take a sample from a population, let's say it's like a sample of size 20 or something. So I've got 20 people in my sample. I've done this well because obviously we want like simple random samples or some sort of random sampling method. Okay, so we've picked a good sample. We've got 20 people in there. When I look at their overall sample statistic, maybe their mean, maybe a proportion of some sort, whatever I'm trying to study, I would get some sort of number from them for the mean or for the proportion. Okay, if I put all these people back into the population again and chose a separate sample, so another 20 people, same size of a sample, again, randomly selected, like real good sample. Out of this group, there's going to be variation because I got different people. Hopefully, it's not exactly the same. But when I take this other sample, I'm probably going to come up with a different mean or different proportion. Again, whatever I'm trying to study, those numbers are going to be different. So sampling variation just talks about the fact that when you take a different sample, even though it comes from the same population, those sample statistics change every time. All right, so since we can take different samples of the same size and get that sampling variation, if we were to take all the different possible combinations of size 20, samples of size 20 from the population, so like every single combination you can imagine from the population, And then we measured each sample's like mean or range or proportion, whatever it was that we were measuring, whatever characteristic that we were measuring. If we took all of those numbers, like each of the sample means or each of the sample proportions or something like that, and used all those numbers together as like our data points, that is called a sampling distribution. And it's like very abstract because it's like how would you ever get all the different combinations of that same sample size from the population? Like physically, it is impossible because if your population is large, like I don't know how you would get that in real life. So I want to do a little demonstration just to like show you a little bit more concretely what this would look like. So I'll demonstrate this using a simulation of SpongeBob's Pretty Patties. So I don't know if you know, there was an episode where he made Pretty Patties. These are the colors. And we're going to pretend that he has 600 of them. So 100 of each color. So the proportions of each color then should be 1/6, or yeah. If you want that as a decimal, like 16.7%. So in this example, the population proportion of purple patties is 1/6. So we would describe this as P equals 1/6, lowercase p, because it's a population proportion. So let's say I go up to SpongeBob and I'm like, okay, I need an order of 20 patties. So he randomly chooses 20 patties for me, whatever color happens to be in those 20, cool. So we're going to specifically, just for the sake of this example, like pretend I really, really love the purple ones because, you know, they match my purse. So I want to know the proportion in the 20 patties that I get, what proportion is going to be purple. So let's say in this first sample, in my first order of 20 patties, I get 6 of them. So this comes out to a sample proportion, a p hat, of 0.3. 6 out of 20 is 0.3. Okay, so let's pretend he made some more. So now he's back at 600 total pretty patties. And I asked for another order of 20 pretty patties. This time, I end up with 2 pretty patties, or 2 purple patties. So that ends up being a sample proportion of 0.1. And let's say I just keep doing this. So I ended up giving SpongeBob 15 different orders for 20 patties, and these were the proportions of the purple patties that I got. So I converted them all into decimals for convenience. And so these numbers right here is the probability distribution for like a very small subset of our different proportions of purple patties. So if I had done this with my 600, like SpongeBob's 600 total pretty patties, and I figured out all the different combinations of 20 different pretty patties that I could get, and then found each of those sample proportions and looked at all of those proportions together, that would be like the full sampling distribution. But right now we just are, you know, trying to do a demonstration, so I'm not going to go crazy here. So what I've done is graphed this out in my graphing calculator. So this graph right here is just all of these proportions. So as you can see, I've got more numbers that are smaller. So these were the proportions of purple patties that were between like 0 and 0.07. So I think I got like 0 or 1 purple patty in my order of 20. And then I have a few here where I got between 0.07 to 0.14 pretty patties, proportion of pretty patties, and so on. And so these are just these sample proportions graphed out. But because all of my sample proportions are changing from sample to sample, this is the sampling variation that we were talking about. And so if I were to actually include all of the different combinations of 20 pretty patties and graphed out each of those sample proportions, this graph would actually look much nicer. Because right now I've got kind of like pretty big variation here. I've got all sorts of different numbers, and with the full effect, it would look much nicer. But even with just this information here, we can still kind of talk about the sampling distribution overall. So whenever we talk about a sampling distribution, it's kind of like back in chapter 1 when we would say like, describe the distribution. When we talk about a sampling distribution, we can still use SOCs to describe it. So we want to be talking about the center, the shape, the spread, outliers not so much just because it's kind of already built into the overall distribution description. So when we talk about a center, we can kind of say like, you know, the average sample proportion is hard to kind of describe here, but like the average sample proportion that I would have gotten would probably be somewhere around here between like 0.14 to actually even between 0.07 to 0.14-ish, somewhere in these two bars, just because we're skewed to the right. So there's the shape. So the center would be somewhere over here. Its spread, we can use the standard deviation to talk about. And when we talk about the center, it's usually going to be the mean. In addition to just talking about the mean for the center, sometimes you'll also hear the center being called a biased or an unbiased estimator. So whether you're biased or unbiased is basically saying like how close is your statistic, either whether it was a mean that you were measuring from your population or a proportion or something like that, compared to the actual population parameter. And so this is something that's like difficult to talk about in real life because we would never really know what the actual population parameter is in real life. So we're basically just saying like, if we knew, then would our statistic be actually a good estimator of our population? So when we say it's unbiased, that means like, you know, unbiased is good, bias is bad. So unbiased means that our statistic and our parameter are actually the same, which is great, meaning whatever we got from our sample matches our population fantastically. So this is what we want. When we talk about spread, you might also hear people say whether things have low or high variability. So remember, variability is just like another word like variation or standard deviation, things like that. So low variability means that like the change between the data points is smaller, low. So you have less spread, which means you have more consistent data. And that's kind of a better thing because then you have like fewer outliers, things like that, because that's what would affect the spread. So high variability means that your data is more spread out. All the samples that you got were like all sorts of craziness happening there. You got like at both ends of the spectrum, whatever. So one way to get lower variability is to have larger sample sizes. And this is kind of something we've talked about before. Larger sample sizes in general is better because when you take larger sample sizes, you're less likely to have like crazy outliers that aren't balanced out by like more normal people in your samples. One thing to note though is that larger sample sizes don't fix everything. So if you took a large sample but you got a bad sample to begin with, or like it wasn't random, then you're still going to have bias within your sample. And so if you have bias within your sample, even though it's a large sample, your center is still going to be off from what the population parameter is. So larger sample sizes don't affect bias. Lastly, when we talk about our sampling distributions, the shape. The shape, we know how to describe a shape. However, what we want then is approximately normal because from all the probability calculations that we've done, approximately normal is when we can actually calculate probabilities nicely. So that's why we want approximately normal. So as we go through our chapter, we will kind of talk about how we do these calculations, how to get that approximately normal shape, and like what we can manipulate. All right, that's it for this section. Thanks for watching. Bye.